All right. So today we're going to start with the concept of NMR. What's going on with this pen? And NMR is short for nuclear magnetic resonance. I bought a new pen. It worked fine the other day. Now it's working like crap. Such is life. So nuclear magnetic resonance. So really, when you're doing all of these techniques fall under characterization. Like if you're an organic chemist, one of your greatest tools is an instrument used to characterize your compound or to determine whether or not you actually made what you said you made. So NMR is one way. We've already, and what NMR tells us is what the carbon hydrogen framework is. So carbon hydrogen framework. All right. Mass spec, which we talked about the other day, is size and molecular weight. All right. When we talk about infrared, infrared is telling us about the functional groups. All right. So hopefully we'll get a chance to actually talk about infrared also. We're going to spend a good bit of time on NMR because it's a pretty involved topic. But hopefully we'll get a chance to talk about infrared as well. And then there's another characterization method, which is, let me add another page right quick, which is ultraviolet or UV spectroscopy. So UV spectroscopy, and that tells us if there are any conjugated pi systems present. Right? So those four methods are not all of your characterization methods. There are a bunch of different types of characterization methods for organic, but those four methods in particular are the most heavily used as far as determining what the structure, how a molecule is put together. These are the four main methods for determining that. And so let's jump in. Everybody here has done aspirin synthesis if you took Organic 1 lab. And so what you did with aspirin synthesis, I'm going to draw it over top of here. You took salicylic acid, which looks like this. And you reacted it with acetic anhydride, which looks like this. And when you did that, you actually acylated this hydroxyl group, right? So in the product, it looks like this. And so with this product, I'm gonna run out of room, hold up. All right, so with this product here, you have O. So you added a acetate group onto that, and then the acid is still here. We get my life right one day. Okay. All right, so one of the ways to determine that, what's one of the things that we did, if you made this in lab, what's one of the techniques that we use to determine the identity of the compound? Anybody remember? We did a bunch of stuff.
Was one of them the crystal?
Say again?
Was one of them making the crystals?
Okay, so we crystallize, we recrystallize it, that's true. But what did we do after that? There's a bunch of techniques we did. We tested for purity using what? Anybody remember?
The absorbance thing?
Say that again?
The absorbance thing?
No, we didn't do that. We didn't do that. That was in, not for aspirin. But we tested. We tested for its purity with iron chloride. Remember, and if it turned purple or light purple or dark purple. If it was light purple, that means it's more pure. If it was dark purple, it was less pure. Y'all don't remember that? And then we also did the melting point. So if the melting point matched up with what was already reported, then that was a way to determine identity and tell whether or not you made aspirin. And then we also did NMR, right? So one of the things that NMR tells us, again, is the carbon-hydrogen framework of any molecule, right? As long as it's got hydrogens and carbons, we can take an NMR. Now, let me say this real quick. There are many types of NMR because it's a nuclear type of spectroscopy. So you can do oxygen NMR, fluorine NMR, phosphorus NMR, silicon NMR. I mean, you can look at a lot of different types of nuclei, right? But for aspirin, we did what's called proton NMR, or 1H. Freaking waste of money. Sorry. NMR. Threw my whole game off. I was really looking forward to using this new little stylus. Cheap. I'm sending it back. I don't know what happened either. No, I didn't drop it. Anyway. All right. So proton NMR, right? That's what we did. And what proton NMR allows us to do, which I'm going to talk about, I have a PowerPoint, but I wanted to use this as the introduction. What proton NMR allows us to do is find out the location, the number, and the neighboring environment of any hydrogen. I'm gonna write that down. I'm gonna add another page right quick. All right. So come on now. Go back to that. So we did proton NMR. So that you'll see it written like this, 1H NMR. What it allows us to determine is the location. So electron rich or electron poor environment. Right? It allows us to determine the number. So the number of protons, and you do that using a technique called integration, which we're going to talk about. And it also allows us to determine the environment or to connect. Let me not say that. Let me not say environment. Let me say connectivity. Right. So with the connectivity, that's going to be shown in the splitting pattern. or what we call the multiplicity. And we're going to talk about all of this in detail. Right? So NMR allows, the proton NMR allows us to determine all of this information from a spectrum. So let's look at the spectrum that we took, and this is a sample. This is actually a real NMR that we took. So the smaller peaks are salicylic acid, and let me zoom out to here. I want to zoom out to here on purpose. So remember, this is salicylic acid. I'm gonna draw that in a different color down here. Change that pencil. Just gonna do that. So that's salicylic acid, right? What you'll notice on the ring, because all these protons are, these are all the protons that are going to show up for either one of these compounds, except for aspirin, which I'll show you in a minute, but there's a reason for that. If you look at salicylic acid, right, on the ring, you got hydrogens on the ring here, 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 and here, right? So you got hydrogens on the ring. You have a hydrogen here, and you have an OH proton here. The OH proton is iffy. Sometimes it'll show up, sometimes it won't. It depends on the field strength of your magnet and all that stuff, right? But the other protons, these aromatic protons, they definitely show up. And they show up in a certain range, somewhere between, let's say 7 and 8.5 parts per million. That's the scale for proton NMR. It's in parts per million. All right. So what you see now here, all these little peaks here, 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 and here, those 4 peaks, 4 signals correspond to the 4 hydrogens that are on that aromatic ring. So if you take an NMR and you have an idea of your structure, you can actually confirm what the structure is based on the NMR, right? There's another peak that's all the way out here, and this is common. This is your carboxylic acid peak. That carboxylic acid OH, it always shows up out somewhere past, a little bit past 10. All right. So all of those hydrogens on the ring have a signal. The carboxylic acid OH is going to have a signal. And the hydroxyl proton is also going to have a signal. But again, sometimes you can see it, sometimes you can't. It just depends. Are y'all following that? So when we do proton NMR, we're looking at hydrogens, right? Any questions about that? We're going to talk about the aspirin one also, and we're going to point the peaks out for that too. And then we'll jump into this PowerPoint. I just wanted to introduce it with something that you've already seen before. Okay, any questions about the signals? Every one of those hydrogens is going to give its own signal because they're all what we call non-equivalent. All of the H's here are non-equivalent. Right? If they're not equivalent, then they're going to give different signals. All right. So for aspirin, let me see if I got it. Yeah, I got it on there. Let me put the structure for aspirin here, and we're going to point out the signals. I'm going to change the color on that. All right, so that's and this is a CH3 right here, by the way. I don't want you to lose that, all right? So let's think about this. What should we see in this spectrum? How many signals? Remember, the ring still has hydrogens on it. Let me put them in. One here, 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 and here. And all of those hydrogens are different. That means they're not equivalent. So we should see how many signals for that ring based on what we just saw.
4.
4 signals.
5.
Why do you say 5?
I said 5 because I was looking at the CH3.
Yeah, no, I was just talking about the ring. You're right. That's
okay.
definitely going to give a signal. You're absolutely right. All right. So here now you got 4 signals for the ring, and then you should see a signal for this CH3. That's right. So that's a total of 5 signals. And then what else? What did we see up top? You should see the carboxylic acid signal too. Is that right?
Yes.
Yeah. And if you look at the spectrum, you can see down here about 11, close to 11, you have a peak for the carboxylic acid OH group. That's 1 signal. In the aromatic region, you have 1, 2, 3, 4 signals for the aromatics. I'm gonna talk about that big peak in a second. Then you still have some little leftover residual salicylic acid. This is after purification, so it's still a little bit left. Probably would do better recrystallizing that again, right? But you see your 4 aromatic signals, and then for your CH3 that's attached to a carbonyl, you see a signal down here at about 2.4, 2.3, 2.4, right? So this is 2.3 parts per million. This is 10, I'm gonna say 10.7 parts per million. This is the location. And then all of the aromatics, I'm just gonna say they're located between, let's see, 7 and 8.2. So 7 to 8.2. Let's just do that. So the aromatics show up between 7 and 8.2. So you have a total of 6 signals because you have 6 different types of protons in that molecule. Is that making sense? So every non-equivalent proton has its own signal. Right, so every proton that's not equivalent is gonna have its own signal. So let me ask this question and see how you think it. What can we say about the protons, the 3 hydrogens that are on CH3? What can we say about them?
That they're equivalent?
Exactly. Those 3 protons are all the same, so they're all gonna fall under the same signal. So what we could say as a generalized statement is that equivalent protons all show up under the same signal. So non-equivalent protons give their own signal, and then we can say, as an addendum to that, that equivalent protons I'm just gonna say, because it's right on the line, I don't want it to cut off in the notes. Right, so equivalent protons are going to be represented by the same signal. All right, so I said there was something else I wanted to bring out in this, and it's this big giant peak right here at about 7.2. That's your solvent peak. right? That's your solvent peak. For most of your NMRs, you're gonna have to do, if you're doing proton NMR, you do it in a deuterated solvent, or solvent with deuterium. That's a hydrogen isotope. You do it in deuterium. So this peak at 7.24 is CdCl3, deuterated chloroform. Right, CdCl3. That's always going to show up in the same place. Right. So one of the things that, again, you can get the location, the number, and the connectivity based on the NMR spectrum. Look at where the aromatic protons are relative to all of your other protons. They're further towards 10, right? Your scale for proton NMR spectrum is from 0 to 10, right? And so the further you go away from 0, that's called downfield. We're going to talk about that in a minute. The closer you come to 0, that's called upfield. So your aromatic protons are showing up downfield, further downfield, right? Your carboxylic acid proton is way downfield. And then the acetate proton is a little bit further, what we call upfield. And then there's one other thing on this spectrum I want to show you, and it's right here at 0. So at 0, that's your reference peak, and that reference peak is based on TMS. It's a tetramethylsilane, so it's a I'm gonna just write it in condensed form. So it's a silicon with 4 methyl groups on it, and those protons on those methyl groups all show up. They're all equivalent, and they all show up as 0. So TMS is the reference compound for your proton NMR, right? You can always calibrate your spectrum based on TMS. All right, any questions so far?
No, can you scroll down so I can write the every non-equivalent proton?
Is that good?
Yes.
All right. Any questions about anything? We're going to talk about, if you notice, if you can look at that little zoom in section from 7.2 to about 8.2, 8.3, how the peaks they're not just single lines. We're going to talk about why that is. We're going to talk about why some protons are further downfield and further upfield, all of that. But I wanted to introduce NMR to you using something that you're already familiar with. We've already made aspirin. And then you probably, if you took my class for part 1, you had to include the aspirin NMR spectrum in your lab report. Right? You probably didn't know 100% what you were looking at, but we're gonna get more clarity on that. All right, any questions? Any other questions? All right, let me switch this to this PowerPoint, and then we're gonna jump in and go do some examples in there. Let's see. All right. So we already talked about some of this stuff. I'm just going to kind of reiterate it. And so you see that the proton or NMR spectrum is going to tell you, again, this is the biggest takeaway from this, is that how many non-equivalent types of protons are there in a molecule. That's the biggest takeaway. if you know that, then you can use an NMR even to determine a structure. If you have a molecular formula, if you know how many signals are there and how many signals are generated, that'll tell you how many non-equivalent types of hydrogens you have, which in turn will allow you to build a structure based on the NMR spectrum. If we had time, we would do that, but we won't have time to do that. When I was an undergrad, that's how we just got thrown to the wolves. We learned a little bit of the technique. Of course, we didn't have an NMR when I was at Alabama State, but and that was one of my goals when I came to Tuskegee, is to make sure we got an NMR. But we were given a molecular formula and some other spectral data and NMR, and you have to build the structure based from the NMR. And it's not that difficult. It just it's time consuming, and we won't have time to do it that way. So it's going to tell you about the environment, where it is, upfield or downfield. If it's in an electron rich or poor environment, it's going to tell you the number. That's what we get from the integration. And it's going to tell you the connectivity. That's where you get the splitting patterns from. All right. So again, upfield is closer to zero. Downfield is further away from zero. And that's very nuanced. Something can be considered an upfield shift if it goes from 2 to 1.99 or 1.97 or 1.95. It doesn't have to be a big shift. It can be a small shift and still be considered an upfield or a downfield shift. And so this molecule, you can see, it should give us how many signals? What do you think?
I would say 1
You say
for the
5?
proton.
5.
Right? So let's look here. Let's look at it. So you have a hydrogen here, right? You have a CH3 here, a CH3 here, 2 protons here that are not shown because it's skeletal, and then a CH3 here. So with that, you should see 5 signals. Each one of those, none of those protons are the same. They're all non-equivalent. Even the 2 CH3s are non-equivalent, right? If you swapped out a hydrogen on this carbon with another atom, or swapped out a hydrogen on this carbon with another atom, you're going to get 2 different constitutional isomers. So that we're going to talk about the test for equivalence shortly. But that's how you can tell if 2 protons or sets are equivalent or non-equivalent, right?
Did you repeat that, Dr. Russell?
Yeah. So in order to determine equivalence, I got a whole slide on it. Well, so in order to determine equivalence, like let's say you want to look at, let me see if I can annotate this. So these protons right here, and you want to compare them to these, right? What you would do, now I'm saying definitively that those are non-equivalent, right? But if you didn't know that they were non-equivalent, there's a test. If I took one of these protons off and replaced it with a chlorine, and then I went back and took one of these off up top and replaced it with a chlorine, and I compared the 2 structures. If the 2 structures are not identical, that means that the 2 hydrogens that I'm comparing are not equivalent. Right? We're going to talk about it in a minute. I have a slide for determining equivalence and all that stuff. So it's going to click, right? But we got 5 signals because we got 5 non-equivalent protons. And then notice each one of those signals is in a different place, right? They're not all bunched up in one area. They're all in different places because they're all in different chemical environments. Some of them are in more electron-rich environments than the other, right? And so because of that, that's why you see some of them showing up downfield and some showing up upfield. The ones that are upfield are in slightly more electron-rich environments. The ones that are downfield, slightly more electron-poor environments. So it just depends. So that, but we can determine all of that based on the NMR, this spectrum, right? Let me see. Oh, hold up. I got to turn this off. Any questions before I take this off?
No, sir.
All right. So you can see all the way that little downfield shift. You notice that even even though it's a downfield shift, it corresponds to one of these protons in this molecule. And what you'll notice is that some of the signals are not just single lines, right? Some of them are split up into 2 lines. This one is split into 4 lines. And so what that tells me is the connectivity. I can determine what a given proton is around or what's connected to the carbon where that proton is. I can determine that based on how that pattern is. If it's split into 4 lines or 3 lines or 8 lines, I can determine that piece of information tells me what that carbon, where that proton is bonded to, right? So we're going to talk about that. There's a rule you can apply. It's called the N+1 rule. You apply that, and it's going to tell you whether something is going to be a triplet or a doublet or a singlet or a quartet, so on and so forth, right? But all that information we can glean from the NMR spectrum. All right. Any questions before we move on to the next slide? All right. So again, we talked about this. Nuclear magnetic resonance. That's what the acronym is for. And it tells us about the carbon hydrogen framework, proton NMR now. Because again, you could do a lot of different types of NMR. You could do carbon NMR, phosphorus NMR, fluorine NMR. It just depends on what you're trying to determine and what you want to study. So the carbon hydrogen framework of a molecule can be determined by an NMR. It's the spectrum is from 0 to 10 parts per million. And we already talked about the TMS being the 0, right? That's always 0. So you can calibrate any NMR spectrum based on the chemical shift of TMS. And that's what we call the number, right? 2.1, 3.5, that number we call the chemical shift. That's the location of where your peak where your signal shows up. That's what we call the chemical shift. All right. And then what the technology behind NMR is, it uses the magnetic field from a nucleus of an atom. For proton NMR is going to be hydrogen. And we use that, excuse me, to generate a signal, right? So you've all seen, if you took organic lab and you showed up on the day we did NMR, you've seen this instrument before. It's just a giant superconducting magnet sealed up in a canister, right? And that canister is full of liquid nitrogen and liquid helium to keep the magnet cold, right? So you take your NMR tube, which is shown right here, this little glass tube, put your sample in, you dissolve it up, dissolve the sample up first, add it to the NMR tube, and then drop it down into the magnet. So the magnet is gonna have, it has a radio frequency transmitter in it that's gonna transmit this radio frequency energy. So we're gonna talk about how that works. So the theory behind NMR, every nucleus has its own magnetic field that's spinning randomly. And then when you put it into a external magnetic field, which is what the NMR magnet is, we put it into that, the NMR magnet, some of those magnetic fields that are spinning in the molecule are going to line up with the direction of the magnetic field of the NMR magnet. And then some are going to line up against the field. Some are going to rebel. And so that's the purpose of the radio frequency energy. You got to beat the ones rebelling into submission, all right? So this is what this looks like. So you got these random spins all over the place. You apply a magnetic field, and then you see some of the spins, magnetic field is going from left to right. And so some of the spins here line up, they go from left to right. And then the bad children go the opposite direction, right? So you got to whoop them. So that's what the radiation is for. You take the RF radiation and boom, you pulse it. And as you pulse it, the misdirected spins line up or come into resonance, that's where that term resonance comes from. The misdirected spins get redirected and they line up and then everything is in resonance or in harmony. And so then they all, right, have the same direction now, right? They all in resonance. But in between pulses, they relax back, right? And so when you redirect it and then the magnetic field relaxes back, you release energy. And that the release of energy is picked up by a detector, and that gets recorded as what we call a FID, or free induction decay, which I'm gonna show you on the next slide. Any questions about this? So your spins are random, and then you apply a magnetic field, and then some of your spins are lined up with the field, some lined up against the field. Then you pulse them to make them all line up, and in between pulses, they relax back. The ones that were misaligned are going to relax back to their normal state. And then when that happens, they give off energy, and then you pick that energy up in a detector or by a detector. All right. So this is what the FID looks like. It's if you take an NMR, the FID is just basically a graph of an equation, right? And so you have to take the FID and convert it into something readable. And so to do that, you do a Fourier transform. This is all high level mathematical calculations. Don't ask me how it works because I don't know what the exact method is for the Fourier transform, right? But you do a Fourier transform to convert the free induction decay into a readable spectrum, which is on the right side. All right, it's kind of a black box to me because I'm not a spectroscopist, right? Analytical chemists or spectroscopists will spit that to you so quickly. Boom. Okay, this is how it works. You plot this versus this. Boom, boom, boom. But the point I'm getting across is that the FID is unreadable, so you have to convert it into something that's readable. All right. All right. So we're gonna look at a simple example, and from that example, we're gonna learn a lot. We're gonna learn the number of signals, what that tells us. We're gonna learn the location, and we're gonna learn the multiplicity, right? What that means, splitting pattern, right? And we're gonna do it from a real simple example of ethyl acetate, right? So if you look at ethyl acetate, how many signals are in that NMR?
Three.
3 signals, right? So what does that tell me? That tells me that there are 3 types of protons present, and they're not equivalent to each other, right? They're not one type of proton is different from the other 2 types, all right? So when you look at this molecule, you can see, right, that the pink protons are represented by the signal about 4.2. Red protons, which are on the far right on the carbonyl carbon, well, adjacent to the carbonyl carbon, those are represented by that peak at about 2.2. And then the blue protons are represented by the CH3 that's on the far left.
So how do you know which signal is for which proton?
Good question. We're gonna get to that. I'm trying to work you up to that, but there is a way to know. The location is the way to know, right? The location and the splitting pattern. You see how the one that's pink is split into 4 lines, and the one that's blue is split into 3 lines, and the one that's red is only a single line. That tells me that is one way to tell which one is which, in addition to where it's located. All right? Are you following?
Yeah.
Mm-hmm. So there's a couple of ways you can tell which one is which, and we're going to talk about all of that. All right, so what we're talking about now is the equivalence. So we know that we should see 3 signals because each one of these protons or sets of protons is different. Why don't we see another signal or 3 signals for that CH3? Why do we only see 1 signal?
Because when they're equivalent, they all have the same signal.
Right, so if they're on the same carbon and all 3 of those protons are on the same carbon, then they're not going to give separate signals. Just like the CH2 right here is only going to give 1 signal. Even though it's 2 protons, they're going to be represented by 1 signal. And then the CH3 here only gives 1 signal. The way you determine the number of protons that a signal represents is through what's called integration. So you would basically put a curve over each one of these signals and take the area underneath it, and that'll tell you how many hydrogens each signal represents. So if we were to integrate this signal right here, the integration would be 2, because that's representative of the 2 pink protons. And if we integrated this signal right here, the integration would be 3, right? Because that's representative of this 3 protons on this CH3. And if we integrated this signal, the integration would also be 3, because this signal is representative of the CH3 here. All right. So you got 3 sets of non-equivalent protons. And again, the way you determine whether a proton is equivalent or homotopic or non-equivalent, or what we call heterotopic, is to take one of them off and to put another atom in its place. Let me switch back to my iPad and I can show you that right quick, because I know that might sound confusing on the surface. All right, so let me show you. Let me switch to my iPad, and then I'm gonna it's coming. This slow as molasses. And I'll tell you what. All right, here we go. All right, so let me give you an example of that proton equivalence versus non-equivalence. And the test for it. And I'm just going to use the example that we already looking at with the ethyl acetate. So we have this. And let's say for the sake of argument that we want to know if the 2 CH3 groups are equivalent. All right, so what I would do as a test is I would take off one of the protons. So let's say I'm going to remove one of these and put a chlorine in its place, right? So the new structure would be here, CH2, Cl, right? That's a little too close to the edge, hold up. All right, and then by the same token, if I took one of the other ones off on the other side, this is what the structure would look like. So it would be Cl. I probably should have let me just draw it out in Lewis form. That'll make it easier to see. Cl, H, H, And then over here, I'm gonna do the same thing. Now, if we compare those two compounds, right, those two molecules, are they the same or are they different?
I would say the same. It's like a mirror image.
You think those two are the same?
Oh wait, never mind. I was looking at the. Never mind.
Okay, it's all right. Did you hear my voice, like the inflection, like what? He's like,
Right.
no, I didn't mean to say that. Nah, no, but no, they're not the same. If we were to name these compounds, right, they would not be the same compounds. Right, look at where the chlorine is here, and location wise, relative to where it is here. You see what I'm saying?
Yeah.
These are constitutional isomers. Right, so they're not the same. They have the same molecular formula, but they have a different structure. Right, so constitutional isomers. So that's how we test for equivalence. If we got two hydrogens and we're in question about whether or not they're the same, swap one out and stick another atom in, and then swap the other one out, stick another atom in, and compare the structures. If they're not identical, then those two hydrogens are non-equivalent. All right, does that make sense?
Yeah, it does.
All right, so that's my test for equivalence. So when I go back to, here, that's what this example is talking about, right? If you want to, compare these two sets of protons, you stick another atom on the one on the end and stick another atom on this one here, and you compare them, and it's two different compounds. If they're not identical, then they're not equivalent. All right, does that make sense? All right, so let's look at, we got a few minutes left. Let's look at these examples and see if we can figure this out. How many signals would you expect for the top example, the ketone?
3.
3.
Oh
Okay,
wait, 3.
you're right. Right, you have two CH3s and neither one of those are the same. And you have a CH2 here, right? And that's not the same as either one of the other two either. So you got 3 sets or 3 types of non-equivalent protons. And then you also, by default, are going to get 3 signals. Is that making sense?
Yes, sir.
Yeah, it is.
All right. Let's look at the next one. What do you think? How many signals? How many non-equivalent proton types? And then how many signals?
7 signals, I think.
7? All right. So you're saying all of them are non-equivalent, basically. Yeah. 1, 2, 3, 4, 5, 6, 7. And I agree with that. And it's potentially 8, but again, sometimes the OH proton shows up, sometimes it doesn't. It's very difficult to resolve that OH proton as well, unless you got a really super strong magnet.
So don't count the OH.
No,
Like, how do we know when sometimes
we do examples in class, I'm either gonna indicate that the OH doesn't show up or I'll point it out.
Okay.
What about the next one? What do you think? We can end on a high note.
Would it be 6?
You know you got 1 hydrogen on this carbon and 1 hydrogen.
Yeah. Oh, so it'd be 7 again. Wait, 1.
So let's count them. So this, you know, that's gonna give a signal. 1, 2, 3, because you got 1 hydrogen on here. 4, 5, 6, 7.
Mm-hmm.
Right, so that's 7 non-equivalent protons, and they all gonna show up at different places. They're not gonna show up lumped. You've seen that already. They're not gonna show up lumped on top of each other. It's gonna be a nice, orderly, well-defined spectrum. More than likely, sometimes it can get messy, but it'll be a well-defined spectrum with each one of those protons having its own chemical shift. Right, and if you notice, regardless of the fact that this is a CH3 and that's a CH3, they're not the same. Right, they are not equivalent because of
And that would be because of what they're attached to?
yeah, it's the location, what it's attached. It's exactly right. It's a great observation. Everything is attached to something different. The only time you're going to see equivalence is if there's some type of symmetry. And we're going to talk about that later. But if there's no symmetry, you can guarantee that everything in that molecule is going to be, every proton is going to be non-equivalent if there's no symmetry present. All right,
Okay.
we're gonna stop here. We only got like 3 minutes left, and we got another topic. But that's the NMR for that molecule. This is the NMR for the alkene with the chlorine in it, right? And then this is, I thought I had the alcohol in there too. I guess I don't. All right, so we got to stop. We're gonna stop here, and if anybody has any questions, I'll take them now. Otherwise, I'll get to work on posting notes, uploading videos, and all that.
Yes, sir, Dr. Russ. I have a question.
Go ahead.
Yeah, it's about the groups. When will we be actually physically seeing each other on campus?
You talking about for lab?
Yes, sir.
I have to go back and look at the announcement for the date I gave y'all.
I think it was like the 16th or something like that. But I was just saying, like, how do you know which group will go out?
I'll tell you. I'll tell you who's coming. Like every group was supposed to designate an in-person person because we're not gonna have everybody. It's too risky.
I see that. Yeah, that makes sense.
Yeah. Because you know that lab has almost 50 people in it, so we can't have everybody from every group because I'm not coming up in there like that.
I got you. Social distance. Yeah.
So what I'll do